Hello, today I'll be proving Theorem 4.6.2. So what is the theorem? The theorem says that if V was a finite dimensional vector space with bases V1, V2 to Vn, then for any set in V, A is that if the set has more than n vectors, then it is linearly dependent. And the second part says that if it has fewer than n vectors, then it does not span V. Okay, how do we prove this? Let's start with proof for part A. So to prove part A, let's see, we have a basis for V, which is V1, V2, and their Vn. And this is basis for V. And we'll have another set in V, which has U1, U2, up until Um. So there are m number of vectors in this basis, in this set S prime. And this is a set in V, where m is greater than n. So there are more than n numbers of vectors. We have to prove that this S prime is linearly dependent. So let's see, what do we have to prove? If S prime was linearly independent, then this would be true. A linear combination, which is K1, U1, K2, U2, up until Km, Um equals to 0. This homogeneous equation would only have trivial solutions. What that means is K1, K2, Km, if we solve for all of those, we'll only have them equal 0 and nothing else. So we have to prove that this is not the case, because S prime will not be linearly independent. It will be linearly dependent. So what we can do now is that since S is the basis for V and S prime is a set in V, we can write all the vectors in S prime as a linear combination of vectors in S. So we have U1 first, and it will have some coefficient C11, let's say C11, and V1 plus C21, V2 plus all the way up to Cn1, Vn. Same thing for U2, it would be C12, V1 plus C22, V2 plus Cn2, Vn. And then we will have that for all the u's, which goes up until um. C1m, V1 plus C2m, V2 plus Cnm, Vn. Okay, so we have all the u's written as linear combinations of v's. And we'll now just plug all the u's into this homogeneous equation to test that it is linearly independent or not. So if we plug these into that equation, we'll get K1, U1 would be C11, V1, Cn1, Vn. That's K2 times U2 would be C12, V1 plus Cn2, Vn. We'll have Km and Um, which is C1m, V1, Cnm, Vn, and that will have to be equal to 0 vector. So we'll rearrange this, because we can rearrange it this way, which will take out the coefficients, group the coefficients together, and then plot the vector. So vector, we have, for example, C11 K1 plus C12 K2 plus C1m Km. All of these are coefficients of V1, right? And we can do the same with all the V's. So that will be C21 K1 plus C22 K2 plus C2m Km times V2 plus, we have how many V's? We have up until Vn. So for Vn, it would be C1n K1 plus Cn2 K2 plus Cnm Km times Vn. So we will have this. Now we have a linear combination with vector V's. And because V, all these V's, they are a basis for the vector space V, right? This is basis. So they have to be linearly independent. That means that all the coefficients will have will be trivial solutions. So that means these coefficients, this thing is equal to 0, this thing equal to 0, and this thing equals to 0. So from there we'll have a system of linear equations, which is C11 K1 plus C12 K2 C1m Km equals to 0, C21 K1 plus C22 K2 plus C2m Km equals to 0, all the way up till Cn1 K1 plus Cn2 K2 plus Cnm Kn, which is 0. So we have a system of linear equations, and in this linear equation we can see that because C goes up until Cn1, this means there are n number of equations, and K goes up until Km, so there are m number of variables. So m is greater than n, just like we mentioned before. That means this system of equation, if we solve for the k's, have non-trivial solutions. So there is some k that does not equal to 0, so it is S prime is linearly dependent. And that is it for part A. We'll start proof of part B. For part B too, we'll also have the basis be S, V1, V2, Vn. This is the basis for V, and S prime will consist of vector u's, u1, u2, until um, and this is a set in V where m is this time, it is less than n. So S prime, set S prime will have number of vectors fewer than n. And we have to prove that S prime does not span V, right? So what happens if it does span V? If S prime spans V, then all the vectors in V can be represented as linear combinations of vectors in S prime, right? Because that what it means to span V. And all the vectors can also be represented as a combination of the bases. So what that means ultimately, it means that the vectors in the basis v1 can be represented as some coefficient times u1, coefficient times u2, coefficient cm1 times um, because there are m number of vector u's. So we'll have a set of linear combinations for the basis, the v vectors. Same thing for this. Cm2 um. So this will have up until vector vn, because there are n number of v vectors, right? So this is similar to the last proof, where we will write out all the linear combinations. So we'll have something like this. And because we stated that the set S, the v1, v2, vn is a basis, that's right, vn is a basis of v, so it should be linearly independent because it's a basis, right? And that means that k1 v1 plus k2 v2 plus kn vn equals to 0 vector only has trivial solutions. So that should be the case. And we'll check if it is the case. And if it contradicts, then it will prove that S prime does not span V. Okay, so same thing like last time, we'll plug these V's into this equation. What we'll have here is K1 times V1 will be C11 U1 plus CM1 UM plus K2 times C12 U1 plus CM2 UM, and we'll have Kn times C1M U1 to CMN UM. That should be equal to 0. And we'll rearrange this. We get C11 K1 plus C12 K2 plus C1N Kn times U1 plus C21 K1 plus C22 K2 plus C2N Kn times U2 plus the last combination would be CM1 K1 plus CM2 K2 plus CMN Kn times UM, and that should be equal to 0. And from this equation we can get another set of a system of linear equation, right? So the system of linear equations will look like C11 K1 plus C12 K2 plus C1N Kn equals to 0. C21 K1, C22 K2, C2N Kn equals to 0. And all the way to CM1 K1 plus CM2 K2 plus CMN Kn equals to 0. This time, let's see. For this system of linear equations, we have how many equations? We have m number of equations, and we have n number of variables. So, as we mentioned before, m is less than n this time, and because m is less than n, that means that there are non-trivial solutions. That means that set S, which is the basis, is linearly dependent. And that contradicts with our assumption that S is a basis. So it proves that S prime does not span V. And that's it. So this is a proof for theorem 4.6.2. And we prove that if for any set in V with basis V1, V2 to Vn, if the set has more than n vectors, it is linearly dependent. And if it has fewer than n vectors, it does not span V. So how do we apply this? Let's look at some examples. For example 1, let's consider V, a vector space V, which is R2, which is R2. So it has a standard basis 0, 1, 1, 0. So and then we have a set S, which has some vectors. Let's say U1 is 1, 0, U2 is 0, 1, and U3 is 2, 3. So here we can see that the vector space has dimension 2, so there are 2 vectors, and the set has dimension 3. And we can see here m is greater than n. And what we should find from the theorem, that means it is linearly dependent, right? The set S should be linearly dependent. So just to verify this, we can see here, because these vectors are pretty simple, you can see that 2 times 1, 0 plus 3 times 0, 1 is 2, 3. That means 2 times U1 plus 3 times U2 is U3. So U3 can be expressed as a linear combination of the other 2 vectors. That means that S is linearly dependent. Okay, so that is an example for the part 1 of the theorem. And let's consider another example. That would be example 2. And this time V is R3. So the standard basis will be 0, 0, 1, 0, 1, 0, and 1. What is going on? Oh, 1, 0, 0. Okay. And then we have set S, a set in V, which has the vectors U1 is 2, 0, 0, and U2 is 0, 1, 2. Let's just think about this one. We can see that this, the basis vector space has dimension 3. There are 3 vectors, and this set has dimension 2. So the set has less vectors than n vectors. And that should, that means that S does not span V. Let's verify this, right? How do we verify this? If S did span V, then we'll be able to write the vectors in the basis, the vectors in V as a linear combination of the vectors in S. So we'll have, for example, we'll have some coefficient times U1 plus some coefficient times U2 and that should be equal to a vector in the basis in the vector space. So these two are from S, this is from V, right? Let's see. We have this, we can do a system of linear equations. 2, 0, 0, 0, 1, 2. We can write it out as this, right? And from this, we can solve for k1 and k2. And the first equation tells us that 2k1 is equal to 0, so that means k1 is 0. And the second equation tells us that k2 is 0, but so we have k1 equals 0, k2 equals 0, but we have the third equation which says 2k2 is equal to 1. So k2 has to be 1/2. K2 can be 0 and 1/2, so there are no real solutions for the system of equations. So S does not span V. So this is another example for when S has fewer number of vectors and it does not span V. So these are the two examples, and this is a proof, and that's it. Thank you for listening.